Good afternoon. Yes, my name is Alexandra Bourne, and I am excited to be here to moderate the first session of the 2025 ClimateWest Forum. As Liz mentioned, I have a long career already in government, working in water and environment and climate change. And currently, my work is focusing on climate preparedness, adaptation, and building resilience. And in our work day to day, working in this area, we're often asking ourselves the questions, how are we going to protect our land and our people from our changing climate? How are we going to build resilient homes, businesses, and communities? Well, our first step as we think about this is we need to, of course, identify our hazards and then think about our impacts and our consequences. In this session, the impacts of climate change on people and land, we're going to discuss the impacts and the consequences of both people and the environment. And we're going to explore both the physical and mental challenges and help provide some strategies for everyone in the room here on how to move forward, and especially how we're going to engage people from our communities to get on board and building resilience. This session also is going to have a great focus on the youth, which is our future for our provinces, and of course, our Indigenous communities. The first speaker that I would like to introduce for this session is Elaine Barrow from the the Canadian Centre for Climate Services. Elaine has a PhD in environmental science from the University of East Anglia in the United Kingdom, and over 30 years experience working in climate change research, from the development of climate change scenarios for agriculture applications in Europe to exploring uncertainty in climate projections in the Western Canadian provinces. Elaine joined the Canadian Centre for Climate Services as a senior advisor in 2019, and since then has been closely involved in the development of the web portal climatedata.ca. Her presentation today is entitled Observed Climate Change Impacts in the Prairie Provinces and Future Projections. Please welcome Elaine.
Thank you very much, Alexandra. I'm pleased to have been invited by ClimateWest to give this presentation today. I've called the Prairies home since 1999, so I've lived through a number of different climate events on the Prairies. So today's talk, could be very wide-ranging. It could take quite a long time. There's a lot to talk about, but I've only got 20 minutes, so I'm going to get straight into the presentation and really just give you an overview of the key changes and the key projections that we expect for the future. So I'm going to start off with just reminding us all why we're here today, and that's to talk about resilience to climate change. You'll see from the slides upcoming in my presentation that the climate of the prairies and of Canada has already changed. Those changes are due to the human influence on climate, and we're going to see the climate continue to change in the future. So what sort of climate we will experience in the future will really depend on how well or how successful we are at reaching net zero and how quickly we can reach net zero. Once we get to that point, our climate will stabilize at that point in the future. And this is basically what the graph is showing here. So the black line shows a trajectory of climate through the observed period and right up into the future. 2 points on that trajectory. So in 2010 and in 2100, carbon dioxide emissions were cut to zero. And then the climate models just left to run. So the climate evolves naturally out into the far future. The yellow line, which we've added in the middle, shows roughly the global average temperature that we would expect to see if we're successful at reaching net zero in about 2050. So what you can see from this graph is that we're not going to be returning to the climate of today. And so it's really important that we try and reach net zero as quickly as possible so that our climate is not as different as it could be if we take a long time to do that. And so this really does iterate that it's important that we start to consider how we can adapt to future climate as soon as we can. Okay, so I'm going to start off with just summarizing some of the key observed changes that we've seen over Canada and the Prairie provinces. And then I'm going to go into some future projections. If we have time, after I've gone through all of those, I'm going to outline some data and tools and a little bit about climate services. So everything that's to support adaptation planning. So let's start off with our looking at observed changes in temperature and precipitation. And I'm just going to explain a little bit about the map that you see here. You're going to be seeing several maps, so I want to make it clear exactly what you're seeing. So each map that you'll see shows the trend in either temperature or precipitation change. The changes have been calculated relative to 1961 to 1990. And then the trend in those changes is calculated across the whole period of record. And that length of record for temperature is 1948 to 2023. And for precipitation, it's 1948 to 2018. And you can see on this map here, which is the annual average temperature change, that there's some area of stippling just to the east of Hudson Bay. Where you see stippling on the map, that indicates that the trend in the variable that we're looking at is not significant. So where we've just got plain color, the changes that we're seeing are significant, and where there's stippling, they're not significant. So we don't have enough information yet to determine whether or not those trends are really robust. Okay, so for annual average temperature change, we've seen increases in temperature across Canada, across the prairies between about 2 or 3 degrees Celsius. Okay, we've seen most of the change in our winter minimum temperatures, so our nighttime low temperatures across the prairies have warmed by about 2 to 3 degrees Celsius, and they've warmed more than our daytime high temperatures, so our maximum temperatures, which have warmed about 1 to 2 degrees Celsius over the 75-year period of record. You can see from both of these graphs that the prairies in northern Canada are warming more than the rest of Canada, and the lack of stippling indicates that these changes that we're seeing in the prairies are significant. So the warming that we've seen is strongest in winter. And again, particularly on the prairies in northern Canada, it's warming faster than the rest of the country. We're seeing warming more in our overnight low temperatures than in our daytime high temperatures. That's the same in the winter as our annual picture. We can zoom in and look more closely. So this is a time series for the changes averaged for Saskatchewan. So this is the increase in annual average temperature. The blue line shows the temperature change relative to 1961 to 1990 on a year-by-year basis, and the red line is the trend. So we can see for Saskatchewan that annual average temperatures have increased by about 1.8 degrees Celsius over our 75-year period of record. Alberta's warmed slightly more, about 2 degrees Celsius, and Manitoba slightly less at 1.5 degrees Celsius. But what's really interesting from this graph that you can see is the variability, so how much the values change from year to year. We live in one of the most variable hydroclimates in the world. It's continental climate, so we see a huge range in temperature between winter and summer. Our climate's also influenced by events that happen elsewhere in the world. So events of tropical Pacific origin, things like El Nino, La Nina, that all add to this variability that we see in our climate. And one of the results of this variability is that you may not feel that you've experienced this warming trend just because on a year-to-year basis, temperatures can change so much. But this warming is impacting our climate, and it's impacting our extreme events. So moving on to precipitation, as I think most of you know, precipitation varies much more widely in space and time than temperature does. And this makes it more difficult for us to identify really robust trends. And you can see that on this map simply by the increased area of stippling compared to the temperature maps that you've just seen. So although if we look at Canada as a whole, temperature has increased, the actual changes across the prairies aren't that significant. At the moment, we still don't have enough information to say, yes, definitely this particular trend is statistically significant and robust. But what you can see in our winter precipitation picture is that there are two areas of significant change. One's in the north, where we're seeing increases in precipitation over our 75-year period of record. And the second one is in the southern prairies, where we've seen significant decreases in winter precipitation. And this winter drying is consistent with changes that we've seen in the storm track. Storm track has moved northwards, and winter cyclone activity has also shifted further north, leading to this drying in the southern prairies. So if we have a closer look in this case for Alberta, so Alberta's seen the most significant decrease in winter precipitation, and averaged over the province, it's about a 25% decrease in precipitation. Again, the record is dominated by this really large year-to-year variability, which can mask this trend. Saskatchewan, also, we've seen a decrease in precipitation, not quite as severe. And by the time we get over to Manitoba, there's really not a significant trend at all in the data. So for summer, you can see that most of the trends highlighted here aren't significant just by the amount of stippling on the map. We do see some increases in precipitation, summer precipitation, particularly in central northern Manitoba. But for the southern prairies in Alberta, there's really no significant trend showing up for summer precipitation. And again, we can zoom in and look at those province in particular. So Saskatchewan again, Alberta, there's almost no change in summer precipitation, increase in Saskatchewan by about 14%, and then by about 20% when we get to Manitoba. And the changes in Manitoba are significant compared to the other provinces. Again, a lot of year-to-year variability, which means the trend can be masked. So those are the key changes that we've observed. I'm now going to move on to future projections. And first of all, I just want to give a quick little reminder about emissions. I think everybody knows that greenhouse gas emissions are driving our future climate, but you might not be aware of the emissions scenarios that we use to examine what this may mean for our future climate. So at the moment, the latest set of emission scenarios that we use in climate modelling are known as shared socioeconomic pathways, or SSPs. There are 5 main pathways, of which 4 key scenarios are used by the climate modelling community. And you can see the global mean temperature change associated with those 4 scenarios in the graph over on the right-hand side. So we've got low emissions SSP1 2.6 in blue at the bottom, going through to very high emissions SSP5 8.5 in dark red at the top. And often when you're looking, if you're reading about climate impacts and climate impacts assessments, you'll see high or very high emissions scenarios used, simply because the climate response is the strongest in those emissions. But best practice is really to use a whole range of emissions in any work that you do. Having said that, if you're thinking about mid-century conditions, so around 2050, there's really not that much difference between the 4 emission scenarios, and they only really start to diverge and become noticeably different as we approach end of century conditions. All of the scenarios that I'm going to show you today, the projections that I'm going to show you today, are based on SSP3 7.0, so a high-ish emissions scenario. And so I'm also going to be showing you a number of maps, all of them taken from the web portal climatedata.ca. And all of the projections that I'm showing you are median projections. So we look at a number of different climate models, an ensemble of climate models, and we take the midpoint of those model results. And all of the models that we're looking at have taken part in the latest phase of the coupled model intercomparison project which is known as CMIT6. On the left, we've got maps of the actual temperature, in this case, annual average temperature values. And on the right, we've got the change relative to 1971 to 2000. All of the maps that I show you are for end of century conditions, so the last 30 years, 2071 to 2100. And you can see that for the Prairie region, annual average temperature is projected to increase by about between 3 and 6 degrees Celsius under this particular emissions scenario and time frame, and slightly more in southern Saskatchewan and Manitoba. So we can zoom in and have a look at those projected changes in a bit more detail. This shows the time series basically for the 4 different emission scenarios averaged over Saskatchewan. So we've got our low emissions in blue through to very high emissions in dark red, and the grey shaded area and the black line on the left represent the historical conditions. So from low to high emissions, we're looking from increases in annual average temperature from between about 2 up to between 8 or 9 degrees Celsius at the end of the century. I've added generational timelines to the bottom of this slide, this figure. So we've got three lines, basically. The top one represents the older generation, and basically, of which I'm part, of basically indicating that we've lived through a climate that's quite different from what's projected to happen in the future. Today's adults, so those on the middle line who were born around 1990, say, by the time they reach the end of their life, they're going to experience a climate that is different from what they experienced in their childhood. And then finally, the last line, we've got today's children. So those born today, by the time they reach the end of their lifetime, they will be experiencing a climate that's very different from that of their grandparents. And this really serves to stress how important it is that we try and reach net zero as soon as we possibly can, so that that future climate is not so different. You know, the earlier we act, the lower the climate response will be to our emissions. This also serves to show that it's really not, we really can't continue to base actions on historical climate. The future climate is going to be different. So we need to consider that in what we're doing, and we can't base actions on historical information. So let's have a quick look at our winter minimum temperature. So if you remember back to the observed, this is where we've seen the most or strongest observed changes. So the projections are also showing continued warming. So by the end of the century for the Prairie provinces, we expect our nighttime low temperatures to increase between about 5 to 8 degrees Celsius under this scenario. So slightly less in the southwest, slightly more in the northeast. And this means that we'll continue to see loss of cold. So we'll continue to see fewer days with lower temperatures below -15 or -25, for example. Okay, we'll skip that one. So our summer maximum temperature, what's going to happen to our daytime highs in summer? Again, we're going to see increased warming also by about a similar amount, 5 to 8 degrees Celsius, slightly lower in the northwest of the region. And this means that we'll expect to see more frequent and severe heat events, and we may experience events that we haven't occurred in the past. The humidex is an index that we can use to investigate extreme heat. And this particular image is showing you the projections for humidex greater than 40. So humidex combines the effects of temperature and relative humidity, and it's an indicator of really uncomfortable summer weather. We all know how uncomfortable it is when we get humidity along with high temperatures, particularly as we're used to a dry climate here. So a humidex over 30, most people find it uncomfortable. We get to greater than 40 and we can enter some dangerous conditions, and people are really going to have to adapt to what they do under those conditions. I'm just going to skip that one. So moving on to total precipitation. winter total precip. So again, we saw significant changes observed in our winter precipitation. So what will happen in the future in winter? So we see a sort of a west to east gradient. Western prairies, not that much change, plus or minus 16 millimeters or so. And as we move east, increases in winter precipitation, maybe by as much as about 50 millimeters. Summer precipitation, median changes indicate that we'll see drying in the southern prairies, so maybe by as much as 50 millimeters over the summer season. Northern prairies, again, slight decrease or slight increase in precipitation. So what does these projections, temperature and precipitation, mean for drought? Well, one of the indices that we use to look at drought is known as the Standardized Precipitation Evapotranspiration Index, and it's an index that combines precipitation with the effect of warming temperatures. And we can look at drought frequency for different classes of drought. So for example, severe drought is when an SPEI value is less than minus 1.5. And you can see from this image here, which shows the frequency of severe drought at the end of the century, from low emissions on the left through to high emissions on the right-hand side, that the southern prairies at the end of the century, they're projected to be in severe drought conditions about half of the time. Okay, and sort of drawing to a close here because I can see cards being flashed up. One of the things I wanted to talk about was a recent development that's from Environment and Climate Change Canada, and that's the ability to see how human-caused climate change can increase the risk of extreme events. And so there's the Extreme Weather Event Attribution Team of ECCC piloted a study last year on heat waves to look at how much human activity has changed the chance of a heat wave occurring. And this is what you can see in this image here. If you zoom into Saskatchewan, you can see that there was a heat event in July last year that was about 8 degrees warmer than we would expect for the time of year. The Extreme Weather Event Attribution Team have used climate models to determine how much more likely that event was because of the human influence on climate. And they determined that it was much more likely, so between 2 and 10 times more likely to occur because of our activities that have already occurred and changed our climate. And this sort of information can put extreme events into context, and they can also support informed decision-making and help tell the climate change story. And I think I'm going to finish it there. I was going to talk a little bit about climatedata.ca. My colleague Casey will be telling you in a bit more detail about that tomorrow. But if anybody has any questions, I'm happy to answer them. And also I'm around for all of the forums, so I'm happy to touch base with anyone afterwards as well.
Hey, we're going to have some time for a few questions. We'll do a few questions in the room, and then we'll take a few questions online. I see Hank has a question.
Can you flip back to that slide? Because you said something that was quite remarkable, and I just want to make sure I got it right. And the attribution for that study is right. You said by the end of the century, the southern prairies will be in severe drought 50% of the time. And that's the source of that is TAN 2024. Okay, you got that, Mr. Tefts? Thank you. Thank you very much. I just needed to clarify that point. Okay, so that's published. Okay.
Let's take another question from the room.
Actually, really glad that the previous speaker asked a related question with regard to the SPEI. You know, not just specifically to the SPEI, but with a lot of these climate parameters that's being projected or downscaled, we reasonably have a way to actually predict this and present this data. I think where the difficulty comes is actually how would for instance, a business owner or somebody whose own assets or in the agricultural industry interpret this data and to translate it into something that they can relate to. Can you speak to how to, you know, does ClimateData.ca or your organization provides any guidance in how to help them understand the impact, for instance, of the change in SPEI?
Yes, we do I was going to tell you that we were actually updating the drought projections. So what you see here are the latest drought projections from the CMIP6 climate models. On climatedata.ca, we have at the moment some limited information about SPEI, but we do provide some guidance about how the different drought severity levels can be interpreted. So we can, we can say it's become 1 or 2 times more frequent, things like that. So we try and move away a little bit from the actual values and interpret them in a way that be useful for a farmer or, somebody who works in agriculture. So we do, it's a complicated index. It takes some understanding, but at the same time, it's also a very useful index because it doesn't demand a huge amount of data. And that's one of the problems that we run into with drought, is that it's so dependent on, not only temperature and precipitation, but sunshine and wind speed and things like that. And this particular index actually does a pretty good job at reproducing observed drought and also simulating it into the future with limited data. And as I say, we do have some information about how it can be interpreted, and we are working on further information to just simplify it. So we're giving sort of key messages rather than giving lots of numbers, and that will help people understand and use the information.
Thank you. I'm glad to hear that's a really important piece.
Thank you.
Is there a question online someone wants to ask? Perhaps we'll go there for the next one. I think this might be our last question.
Okay. Which one? Oh, I'll do the 30-year period ones. I did wonder whether I get some questions about the 30-year periods. So when we're looking at observations, to see the most, or to see change, we try and go back to a time period where there was less change than we see today. So 1961 to 1990 is a time period that's commonly used to compare observations to, so current observations compared to that particular time period. As we move forward in time, that particular 30-year period becomes less and less relevant to people today. Some people were born after that period, so they don't know what it was like in 1961 to 1990. And we tend to move forward in 30-year periods. And we could calculate the projections that are on climatedata.ca, for example. We could calculate those changes relative to 1961 to 1990. But we've moved it forward to 1971 to 2000, and we will also be giving the option for the changes to be calculated relative to 1991 to 2020. So 1991 to 2020 is the most recent climate normal period, it's called, that we have. And so there's 2 sort of points of view of whether you want to try and use a 30-year period that has as little climate change in it as possible as your reference. So 61 to 90, 51 to 80 are those time periods, or further back to pre-industrial. Or we want to use a time period that's relevant to people, so most recent time periods. So we do see differences, and that does make it sometimes complicated, or you have to pay attention to which baseline period has been used to calculate changes by. So yeah, there's sort of lots going on. So you just need to pay attention when changes are cited, what baseline period is being used.
All right, I think we can squeak in one more question. Do you have a question there, Michael?
Thanks, Elaine. I've just been doing a lot of reading in the last 2 or 3 weeks about AI and data collection. And when we're trying to get to net zero, what I'm seeing and hearing is that now that we are in this age of AI and collecting data, that they are going to be using up 2 to 3 times as much carbon and putting it out into the atmosphere as they have up to today, that this is going to be increased by, say, 3-fold, if not more. And it's the big data collection centers. Are you putting that into your projections, and are you working on that? Or is this something that would be new out there that we're going to have to start looking at?
It's not actually directly included in the projections in that, as far as I'm aware, I mean, I don't know all of the intricacies of the different emissions scenarios, but AI itself and the amount of energy that it uses, if that energy use becomes substantial, then we would need to start looking at higher emissions scenarios. That would be how we would factor it in to the projections that we use. So very cognizant of the fact that AI does use a phenomenal amount of energy. I don't know that everybody's aware of that, but it does mean that, if we want to try and include that, we would probably be looking at a more, an emissions scenario that's got higher greenhouse gas emissions than one of the more moderate ones. But there's the whole sort of science of emissions scenarios is a completely different subject, and that feeds into the climate model. So there'll be people working on the emissions modeling that we can update the information in those emission scenarios based on what they're seeing in the in the current period. So okay, great, thank you.
Thank you, Elaine. That was wonderful. And Elaine is around for the next couple days. So I'm sure if you still have a question, you'll probably find her around, and she'll be willing to answer some questions.